Okay, so first I have a few announcements. Let's see. So as you know, I finished grading exam 2. Oops, sorry about this. I hear nothing. I wonder, you guys can hear me, right? I do just all have your mic off. Good.
Yeah, I can hear you.
So it's kind of warm in here. Anyway, I graded exam 2 and I did curve the exam, and the mean after the curve was 76.5. And the grades were very high and very low. There was a lot of grades all over the map. Some people really probably were very happy with their score, and some people I'm sure were not so happy. And we're entering into that part of the semester where it's just really like from here on in, it's just really a lot. I mean, I'm just talking about the whole thing, whole school, especially being online. It's very hard to focus, I know, but it has to go on a little while longer. I did find some examples, some students who did not do their own work, and I ended up giving a few zeros and a few warnings on this exam. So I just want that to be said. I do drop a grade, so for some of those folks, it won't matter very much. But I just don't want you to do it on exam 3 because I actually check a lot of those so-called homework help websites. I'm a member of some of them, and I pay a lot of money to be a member. I don't like that. I'm so glad I'm going to cancel them at the end of the year. But it's really disheartening to see problems that I have just made up for this exam on the internet solved. It's just it's really it cripples me. It is terrible. I would have given that exam back days earlier if it hadn't been for what I discovered when I went to grade it. So maybe you haven't noticed, but on the syllabus, exam 3 is actually supposed to be given out tomorrow. And it's on the first part of acids that we have covered. And that's basically up through last class. And then it's also on equilibrium that we covered before then. And I decided to take, I have 4 pages again, but I'm taking out the 4th page. And it's just going to be 3 pages. And I heard from several of you that you liked that index that I wrote, but I wouldn't mind to hear it now again. How many of you think that I should do that again? Should I write the index again? Yes. Or was it just not, worth it to any of you?
I liked it.
You should.
I thought it was helpful.
Yeah. I mean, honestly, I think that I don't understand why anybody would cheat when you have that index, because it's like basically tells you where to go to find the problems that are very similar to the ones on the test. So, all right, I'll do it again. Okay, good. Let's see. All right, I also want to tell you about withdrawing, if anyone wants to withdraw from the course. I'd actually like to turn off the record when I talk about this. All right. And what are the chatting people saying? Okay, good. They like that. Okay, good. All right. So I would be happy to have some office hours for this upcoming test. But honestly, they're not very successful, especially when the weather is good. So maybe it would be better if you just email me. What do you think? Do you want me to have some, or would you just prefer just emailing me? I mean, I could do Friday, like at 4:30, and then sometime over the weekend. So if I could have some replies to that, that would be good. Okay, all right. Anybody want Friday at 4:30? Yeah. Okay. All right. Good. All right. So you know what? Forget Friday at 4:30. You have to email me. And I'm pretty available. I mean, honestly, I emailed people back on Easter. It doesn't matter. I know I have to work pretty hard this next month to get through this. But I'm willing to do that. Anyway, and I have to tell you that I've had so much work to do in the last couple of weeks, last week especially, that I thought of my father a lot. My dad, who my dad was an amazing man. He studied math. He worked at a Chevrolet factory. Was kind of a union organizer for a while. Not really. That's the light version of what he was. But anyway, and we lived in New York City, and he went from being a math teacher at a college to deciding he wanted to work doing physical work and building things. So he put in fire doors on the Lower East Side of New York, all kinds of things. Finally, he moved up to Maine, dragging my mother kicking and screaming. And before he died, he actually farmed sheep. He had a big sheep farm for Maine, and he ran for Congress as a socialist and died of Alzheimer's. But the point is that when I used to call him in college, and I know I've told you this before, but I'm giving you a little more background. Not that you want it, but I don't know, whatever. I'm talking into the microphone, who cares? And I used to call him when I was so behind in college that there's no way I could do all that work. Dad, I can't do it. What am I going to do? I'd be like practically sobbing on the phone. And he would say, Laura, he said, just chip away at it. Just chip away at it. And honestly, I have told myself this like 10 times in the last week, when I knew I had to get those tests graded by the drop date, and I had some cheating and I had to write letters, and I just kept telling myself, just chip away at it. And honestly, I did a huge amount of work in the last week, all by just chipping away at it. So every time I went into my office to work, I told my husband, I'm bringing the chisel and I'm going into the room there. So, all right. So nobody likes my story, but I told it to you anyway. And I am telling you, that is really good advice, that, you don't look at the big picture. Don't look at everything you have to do. Just do one thing at a time, chip away at it. I'm telling you, it's great advice. Thanks, Dad. Yeah. Anyway. Okay. So thank you. Good. Somebody likes my story. Yeah. Anyway, and my dad, he died, and it was so bad. He was so terrible with Alzheimer's when he died that it was just so sad, but terrible disease. I hope we cure it. Anyway, so last time, I've already wasted 10 minutes telling you that dumb story. Last time I talked about weak bases. And I kind of think I went through it very fast, but I want to just go over, just sort of recap that. Weak bases. So, we have this base ammonia, NH3, but that's just, one molecule, but it's really like a prototype. So you can have different groups attached to NH2. We call these R groups. You'll see this all over organic chemistry. And an R could be a methyl group attached to this NH2. Actually, I'm going to tell you about one today, which there's two R groups. There's a CH3 and then another CH3. understand, of course, it's a carbon that's attached to the nitrogen. It's not the H. Sometimes this is written as H3C, just so you see where the attachment is. But we assume you know that, okay? So anyway, here is another one. And so what happens when a proton comes along is it basically goes on to that lone pair there. And these electrons from the lone pair end up forming a bond. So you end up with NH4 plus, okay? That is the conjugate acid of the base ammonia, okay? And just like that, if I had, say, this example here, okay, this is called dimethyl, because this is a methyl group, amine, okay? And if you take dimethyl amine, I'm just going to write it like this. You see that? CH3, 1, 2, NH. And notice it only has one H because it has two methyl groups. Nitrogens are generally bound, usually, not always, to 3 different things and have a lone pair. Okay. Anyway, so this is dimethyl amine, and it is a weak base. It's in the sort of the ammonia class of weak bases. And when you add the H plus, it goes on the nitrogen and you get CH3, 2, NH2 plus. Oh, sorry. I should have written plus water. Yeah. Plus OH minus. And that's how it ends up being a base. Okay. So anyway, because it generates hydroxide that way, but it's from being a proton acceptor. So that's another reaction of a base. You could have, say, an NH2 with a benzene ring. I think I went over this with you last time. This is called aniline, and it is also a weak base. So it reacts with water. This is what we call the base dissociation reaction. Even though it's not really dissociating, we still call it that because that's what we call it for acids. So this is like the base analog. So now the H plus again goes over here. If you're having trouble with these benzene rings, I'm not an organic chemist, so I have trouble too. And now this guy here, what would it be called? I don't know what this is called, honestly. I don't know what the name of it is. I know that it is the conjugate acid of aniline. This is the conjugate acid of dimethyl amine. But actually, this one would be called dimethyl, you don't have to know this, ammonium, because it's got that plus, like this is ammonium. So NH3, the prototype one is NH3 plus water gives you NH4 plus, which is ammonium, which is the conjugate acid of ammonia. And this, of course, is the weak base ammonia. Okay. And all of these you could sort of generalize, and you could say that this is B for base plus water. Okay, I will, just a minute. So the base gets protonated, it acquires that extra proton, and then the OH minus. So I got a question here. Can you explain when the double arrows are different lengths one more time if you get the chance? Okay, so it's when you have an equilibrium, whether it favors the products or the reactants, you simply write a double arrow like that. When I write it like this, it's just because I'm indicating that it favors the products. But this is just a symbol. You would never, you basically use this for equilibrium, whether it favors the reactants or favors the products. When I do this with the crazy shape of arrows, it's just indicating which is favored at equilibrium. So this favors reactants and this favors products. But, you know, if you're reading a book somewhere, unless they're actually illustrating that something favors products or reactants, every equilibrium is written like this. So it's just a representation, and you will never see it like if I write a test question and I have a double arrow, it's an equilibrium. I'm not going to draw it with a big arrow and a small arrow. It's just to show you that not all equilibria are the same. And so something like this would have a K value that was much greater than 1. This would have a K value that was much less than 1. All right, I hope that answers your question. Okay, so, so that's an entire class of weak acids. And I think last class, I did the example of what is the pH of an ammonia solution. So let me see if I think I did that. Let's see, where would that be? Ah, look at that. At my fingertips. I'm shocked. So I went over this example, and you could do this with any of those weak bases. You write the dissociation equilibrium, which is basically simply the reaction with water, okay? You end up with, you add an H and a plus, in this case you get ammonium, and OH minus, and then you basically solve the ice problem. And you need to look up in the base dissociation chart what the KB for ammonia is, and it turns out to be this number here. You could find that in the chart. And again, you have the same condition for whether you can neglect the X. Is the initial base concentration, which in this case is 0.02 molar, is that greater than 100 times the KB? Okay. If it is, you can neglect X. So it makes this problem a lot simpler. You just have to cross multiply here. And relatively easily you could find X, but I want to point out that there is an extra step in this problem that's a little bit longer than finding the X in an acid, in a weak acid dissociation problem. And that's because here the X is not H3O plus, it's OH minus. So when you take the negative log, you're getting the POH. And don't give me this answer here, 3.23. That doesn't make any sense. This is a solution of a base. It shouldn't have a pH less than 7. It should be greater than 7. So don't forget to subtract it from 14. So to find the pH from the POH. And you can see now it's basic. So that's the example I did last time. I might have raced through a little bit, which is why I'm going over it now. So that maybe it's a little bit better, hopefully. Oops, there we go. Okay, so we did this in class. C, Monday, B, Monday, April 5th. Notes. By the way, did I ever start it recording again? I did, didn't I? Yeah, I did. All right. Okay. Okay, so that's a very, a very respectably large class of weak bases. This whole stuff I was just talking about here, this info is for a whole, we call them like a whole class of weak bases based on, no pun intended, ammonia and H3. Okay. So the question is, are there any more? Are all weak bases based on ammonia? And the answer is a resounding no. Okay, they are not all based on ammonia. There are tons of other weak bases. All right, so where do they come from? Well, remember that every weak acid has a conjugate base. Every acid has a conjugate base. Every acid has a conjugate base. But remember, strong acids, and we did this a long time ago, strong acids have very weak conjugate bases so that they're not even bases, they're neutral. Weak acids have conjugate bases that are basic. I know that sounds a little weird to say, but it's true. So let me talk about this a little bit. And I always love to go back to acetic acid. So here I have acetic acid. Anybody know the formula of acetic acid offhand? I'd be really impressed if you knew the formula for acetic acid. What about the abbreviation for acetic acid? Ah, somebody knew it. CH3 COOH, otherwise known as HOAC. But CH3, here it is. C double bond O, OH. This is what we call a carboxylic acid when you have this C double bond O with the OH. Its conjugate base is the acetate ion. And what the acetate ion is, after this H plus is donated, what you're left with is CH3 COO minus. And this is the acetate ion right there. Okay. Acetate ion, acetate, I'm just going to call it acetate, is a weak base. It's the conjugate base of acetic acid. Okay. And because acetic acid is a weak acid, it has a conjugate base that isn't so weak, right? Strong acids have extremely weak. The stronger the acid, the weaker the conjugate base. But when you have a weak acid, the conjugate base is not neutral. It is basic. So acetate donates a proton to water. And look at this reaction. Acetate plus H2O. So if it donates a proton, did I say donates? No, accepts. Sorry. Accepts a proton from water. Oops. Since it's a base, it accepts a proton from water. It becomes, what does it become when it does that? What would the formula be of this with an H added? HOAC. And what else is there? If H plus is taken away from water, you get OH minus. That's right, absolutely. So this reaction, by the way, if you recall just a couple of minutes ago, I talked about how a base reacts with water to give BH plus OH minus. The only difference between that and this is that this has a negative charge. So when the H gets added, the negative goes away instead of adding a plus. Otherwise, it's really the same reaction. This is the base dissociation reaction. But that's not what we call it. When we have an ion doing this, we generally call it a hydrolysis reaction. So it's the hydrolysis reaction, which generally just means reaction with water. So this is a we say that acetate, this is how we would say it, acetate hydrolyzes to produce hydroxide ions and HOAC. Okay. We use the expression hydrolyzes for conjugate bases or for ions that actually react with water and either to produce OH minus or in some cases even H3O plus. That's what the term is. It's reacts with water to produce an acidic or basic solution. I'll give you examples that produce an acidic solution as well. So this is a hydrolysis reaction, but it is really just the base dissociation reaction with something that has a negative charge. So it ends up being neutral when it accepts that proton. Okay, so similarly, I'll give you another example. If we take fluoride, okay. Oh, and by the way, we would call this would be acting as an acid here, this water, we're donating the proton. This would be the conjugate acid of OAC minus. Notice they differ only by an H plus. And this here we would say is the conjugate base to H2O. Differs only by an H plus. Similarly, here is the hydrolysis reaction with the fluoride ion. Why do I think F minus is even basic though? F minus is the conjugate base of HF, so it's basic. Is HF a strong acid or a weak acid? I don't remember, right? Let's go look at the chart. If you don't remember, you look at the chart. So here's the chart. Here's HF, right? This is the chart of acid dissociation constants. All these are weak acids. You don't see HCl on this chart or HBr or any of the 6 strong acids. You see HF here. That's the only acid that's a hydrogen and a halogen. That's group 7, fluorine, chlorine, bromine, iodine. It's the only one that's not a strong acid. It's a weak acid. So because it's a weak acid, it has a conjugate base that is basic. So fluoride is the conjugate base of the weak acid HF, and so it is basic. Okay, so it hydrolyzes. And it accepts a proton from water to give HF and OH minus. So this is the base. This is the conjugate acid. This is acting as an acid. And this is the conjugate base of water. It's conjugate acid of F minus. So here's a question. If acetate and fluoride are bases, what is their Kb, or what are their Kb values? Now, if you go to a table, my table is a very short table. It only has a few listed. But if you go to a table of base dissociation constants and you try to find fluoride or acetate, you will see that they are not there. So bases that are conjugate bases of weak acids are generally not listed in these dissociation charts. You might need to know what that K is. How would you find it out? Okay, that's what I'm going to tell you about next. Okay, so here's I'm going to write it in, how to find out the KBs of conjugate bases of weak acids. Okay, how do you do that? Okay, so what I'm going to do is I'm going to use fluoride as an example. got a nice simple formula, F minus, and I'm going to use that as an example. And I'm going to show you, three different reactions with three different equilibrium constants, okay? And then I'm going to combine these equilibrium constant expressions together to tell you the answer to this question, okay? So these are the three reactions. The first one is the reaction of F minus with water, the hydrolysis reaction. This is the reaction that we want to know the K of. It's this reaction basically right here. Okay, I'm going to rewrite it. So hydrolysis reaction. This is the reaction whose KB we want to know. All right, the second reaction I'm going to show you. Oh, I don't have it listed here. Wait, hold on. Well, I might as well just give you this reaction now. So this is the one I just wrote. F minus plus H2O. Now I'm putting in the phases very carefully because I want to make sure that you know you don't have to put in the water. Goes to HF plus OH minus. So this is the first reaction. And the KB, this is what we want. But what is it? It's the concentration of HF at equilibrium times hydroxide over F minus. Okay, this is what we want. Okay, now let me show you a second reaction. This is related, but not at all the same. This is the acid dissociation reaction of the conjugate acid of F minus, which is HF. So HF, what happens when it reacts with water? What do I put on the right side of that equation? If this is an acid, what does it do? What's one of the products that we'll get here?
H3O plus.
Yeah, that's right. What's the other product?
F minus.
That's right. Good. All right. All right. So what is the K for this reaction? Well, it's the Ka. This is, by the way, this is Kb for F minus, just to be very specific. This is the Ka for HF. So that parentheses isn't multiplication. It's like, it's for HF. And what that is F minus H3O plus over HF. It doesn't seem like we're getting anywhere here. But there's a third equation that's going to bring this together. And that third equation is the auto ionization of water. Okay, which is when you have water plus water, which is two waters, and one water donates a proton to another water, remember? So what do you get when that happens? What's on the right here?
OH minus
And what else?
H3O.
Good. And these are both aqueous. So this KW then is this product. Okay. So here's the great thing. I'm going to put these all together. We have this equation here for the Ka for HF. And we have this equation here for KW. And these are equations, just like any math equation. Because these sides are each equal, I can divide one by the other. So look what happens if I take my Ka Let me just make sure I'm doing, oh, actually I divide KW by KA for HF. So I'm going to divide this equation by this equation. So that's OH minus H3O plus, right? That's the KW equals, that's on top, divided by, and here I'll just put all this stuff, F minus H3O plus over HF. Now, I'm dividing by a fraction. So when you divide by X over Y, you multiply by the reciprocal. So this is just the same thing in the numerator, but now I'm going to multiply, I'm going to reverse this, right? And multiply by the reciprocal. I just want you to watch this. I don't expect you to do this, but I want you to appreciate it. Okay. And look what happens here is the H3O plus cancels. And this is HF OH minus over F. Wait a minute. Did I make a mistake? No. No, that's right. Yeah, good. Now, let me show you this thing here. That's what we want. See that? This. That's what we want. That's KB of F minus. So what I just showed is that KW over KA for HF is equal to KB for F minus. All right, I know that's a little out there. It was 3 equations and all that, but we have this really great result. And this result is completely general. In other words, KW divided by the KA for any acid, any weak acid, is equal to KB for the corresponding conjugate base of that acid. So KB for any conjugate base is equal to KW over KA for the acid. This is completely general. And it's very cool. And it allows us to figure out the Ks, the KBs, for all these conjugate bases when, you know, they won't be in charts and things like that. We simply calculate it from KW and KA, and this is for the corresponding. What does it mean when I write corresponding? So it means it's a conjugate acid. It has to be different. These differ by only an H plus. So this would be the Ka for HA, right? Giving you the Kb for A minus when you divide Kw by it. All right, so I know that's a little cumbersome, but we're going to use it. So let me show you how this works. First for F minus. So for F minus, and then we'll do it for acetate. Kb for the fluoride ion is equal to Kw over Ka for HF. So I know Kw, it's always the same at room temperature. And if I go to my acid dissociation chart and I look up HF, it's 6.8 times 10 to the negative 4th. Oops. Okay. So when I calculate that, I get 1.5 times 10 to the negative 11th. Is fluoride a strong, is it a strong base? Is it strong for a weak base? What does this tell you, this 10 to the negative 11th? You know, fluoride combines with water to give HF and OH minus. So somebody was asking me about the lengths of these arrows, you know. Is this a reaction that heavily favors the products or heavily favors the reactants? Would I draw it like this or like this? Number 1 or number 2? I feel like I'm at the optometrist. Number 2. No, this is a very, very small negative. Well, it's a large negative exponent. It's a small number, right? This is a tiny number. K is much less than 1. This favors the reactants. It would be this one. Okay. Thank you for trying, though. I appreciate that. All right. So we have this new thing now. We have these ions that are conjugate bases of weak acids. And we can figure out their Kb values by taking Kw and dividing by the Ka for the corresponding weak acid. Okay. Now, let me show you how this would work for acetate ion, OAC minus. What is its Kb? So how would I do that? Kb for OAC minus is Kw over Ka for what? Any old acid? No. What do I put in here?
The OA.
Has to start with H because it's a corresponding acid, right? It's HOAC. So when we look on the chart, this is always going to be the same. This is one, I don't have to look at the chart. This one I have memorized. And after lab yesterday, and those of you who do the lab tomorrow, you will have this number in your head perhaps. And it comes out to, let's see, so 5.7 times 10 to the 9 minus 10, excuse me. And again, this is a very small number, which tells you that acetate is a very weak base. Because this does not, because this is what equation does this correspond to is the hydrolysis reaction. Okay, so it's like this. Just heavily favors the reactants. This is much less than 1. But it is still a weak base. You don't have to generate much hydroxide to be considered a weak base. Okay, so suppose I want to actually use one of these ions, one of these chemicals. So let me just say, suppose I want to make up a solution of acetate or fluoride. Okay, can I go to the stock room? Here's my stock room. I have a few bottles on the shelves. Can I go pick up a bottle that says fluoride or acetate? So what's wrong with this picture? What's wrong with this picture? Can I just go get a bottle of fluoride? What is fluoride? It's an ion. How does fluoride come? Give me a compound with fluoride in it. An ionic compound with fluoride in it. Anyone, any ionic compound with fluoride in it. Come on. Now, HF is not an ionic compound, it's an acid. See, if I want fluoride to make a basic solution, I would not be able, yes, sodium fluoride is an answer there. Very good. Okay. What's wrong with this picture is that every time there's an anion, there's also a cation. So you cannot just get a bottle of fluoride. Instead, you could get a bottle of solid sodium fluoride, okay? Or you could get a bottle of solid, I better make it a fat bottle because it's got a longer name. Sodium acetate, or as we use in lab, sodium acetate trihydrate. Okay, this is used in the dilutions lab. Okay, so you can have sodium acetate, solid, but you're not going to just have a bottle of acetate. And that's because, you need the counter ion, you need the other ion, because compounds are neutral, okay? They don't travel alone, okay? So you could find sodium fluoride, or maybe calcium fluoride, or here you could have sodium acetate, or maybe barium acetate. But barium is +2, so you'd need, acetate is -1, so you'd need 2 of them. So these are all the kinds of things you could look for on the shelf if you wanted to make an acetate or a fluoride solution, okay? But generally, these are ionic compounds. However, in the context of a unit on acids and bases, we really don't just call these ionic compounds. We use a special name for these type of compounds, and they are called salts. Okay, well, it's no surprise that sodium fluoride is a salt, right? Sodium chloride is what we call salt. So these are salts. Now, technically, what is a salt? So what is a salt? Well, technically, a salt is the product of an acid-base neutralization reaction that is not water. All right, so let me show you something. Here's sodium hydroxide, okay? And here is hydrochloric acid. You put them together, and this is a one-way arrow because we've got an acid and a strong base. You get an acid-base neutralization reaction. The hydroxide from the base and the H+ from the acid form water, but the other product is NaCl. And this is your salt. So technically, a salt is a product of an acid-base neutralization reaction. You have water plus a salt. That is the technical definition of a salt. However, salts are just ionic compounds. But like a hydroxide wouldn't be considered a salt because it would never be able to be the product of an acid-base neutralization reaction because it has the hydroxide. That ion goes away and becomes part of water. So salts are just ionic compounds. So all ionic compounds, I'm going to say, except hydroxides and also except oxides, are called salts. Okay, So don't worry too much about it. Almost all ionic compounds are salts. It's just a few, these are basic and they're not considered salts. So, so that's one example where you could view that now NaCl is a salt. What if you had this base? This is barium hydroxide and water, and acetic acid, let's say. So we have an acid and a base. What are the products of this reaction? I mean, this is really a Chem 103 question, but what would the products of this reaction be? So what's the first product always in this type of reaction? The essence of an acid-base reaction is the hydroxide from the base and the H+ from the acid, which always gives you water. All right. What's the other product?
BaOAC.
BaOAC, but we have to put a 2 there because acetate is -1 and barium is +2. And we need to even out the charge. So this is a salt. So we have water and a salt from an acid-base neutralization reaction. Okay. So the salt, let's go down a little further. So what I'm talking about now, what I'm starting to talk about is the acidity and basicity of salts. So sodium fluoride has the fluoride ion. Okay. The fluoride ion is basic. So sodium fluoride is basic. It is a basic salt. This go away. Okay. So if you made a solution of sodium fluoride, the pH would be what? Would it be above 7, below 7? What would it be?
Above.
Yes, you will have a basic pH. Okay. Now, here's another salt. Ammonium chloride. Now, how can that be a salt? Well, what if you had an HCl and NH3? This is a base and this is an acid. And it undergoes an acid-base neutralization where the HCl donates a proton to the ammonia. Remember, it has a lone pair there. And you'll end up with Cl- and NH4+. What is this? This is the conjugate acid of ammonia. This is acidic. Okay. So what you end up with is NH4Cl. You could write that together, and that is a salt. And you can go to the lab and you can get a bottle of ammonium chloride. Okay. Now, ammonium is the conjugate acid of a weak base. The weak base ammonia. So it is acidic. So let's try to figure out its reaction with water, its hydrolysis reaction. If it's acidic, what's it going to do with water? What's it going to give? If it's acidic, it means it's a proton what?
Donor.
Yep. proton donor. So that means, what are you going to get on this side? If this donates an H plus, what does it become?
H3O.
Well, that's this product, yes. What's the other product?
NH3.
Exactly. It donates a proton. This is a weak acid. This is this acid. This is acting as a base. This is the conjugate base of NH4 plus. Notice it differs only by an H plus. And this is the conjugate acid of water. Now, chemists, we use all kinds of different language. And I just want to tell you that we would say this is the protonated form. This is the deprotonated form. So we recognize the fact that that there are really two different forms of ammonia. There's the form that's NH4 plus, there's the form that's NH3. One of them is acidic. One of them has the extra proton to donate. One of them is willing to collect an extra proton. Like over here, you could think of the fluoride. Where is it? Did I pass it? Every time you have an acid and its conjugate base, you could refer to the conjugate base as the deprotonated form. And this would be the protonated form. And when you take biochemistry or organic chemistry, a lot of times they use this kind of language. And we don't use it a lot in Gen Chem, but you really should recognize you have these pairs, these conjugate pairs. This one is the conjugate base, it's deprotonated. So the only difference between this and this is the proton. This is the deprotonated form. This is the protonated form. So I'm just telling you that because these terminology is used, and I don't want you to get caught flat-footed. Sometimes we refer to this as the anion, and this is the acid. And later when we do buffer solutions, that's what we do. We refer to the F minus would be the anion of this acid. It's just referring to whether it has the proton or it doesn't. The anion doesn't have it, the acid has it. Just language, really. Just so that when you see it, you won't say, I never saw that before. Dr. Cooley never told me about that. So anyway, the salt, ammonium chloride, and you could it's in a bottle on the shelf in the lab. Okay, it's a solid. It contains the ammonium ion. And since ammonium is the conjugate acid of the weak base ammonia, ammonium is acidic. Okay, so when you have a bottle of NH4Cl, NH4Cl is acidic. If you make up a solution, the pH will be less than 7. Okay. So here's the thing, and it's a teeny bit complicated. Salts, there's thousands and thousands of salts, basically all ionic compounds except for hydroxides and oxides, like can be acidic. There's an example of an acidic one. It can be basic. So for example, ammonium chloride here is acidic. Sodium fluoride is basic, or they can be neutral. Okay, now I've got to tell you how you can figure out whether a salt is acidic, basic, or neutral. Okay, so what I would like to do is go to my next page, because I have something there I'd like to show you that I just want to call your attention to this handout. So we're not going to read the handout here, but I want to show you that I have a handout. This is in the packet. This is in the activities packet for this chapter. For unit 6, not chapter 6. Okay. And it talks about what a salt is. So, you know, you're not going to find a lot in the OpenStax book about salts, but I wrote this out. I think it's helpful. It goes through different reactions and it gives you the summary of how to figure out if a salt is acidic or basic or neutral. Okay, so now I'm going to actually tell you. I just wanted to call your attention to this. You can go read that, but I'm not going to just tell you, you know, I'm not going to stop there. I'm going to tell you that salts, I wrote this already, but I'm going to put it here too. Salts can be acidic, basic, or neutral. How to figure out what they are. Okay. So this is what you do to tell if a salt is acidic, basic, or neutral. Okay. You must see if it has these things. So here's one thing. If it has an anion, remember that's the negatively charged ion. If it has an anion that is the conjugate base of a weak acid. If it has an anion that is the conjugate base of a weak acid, then the salt will be basic. And I'm actually, what I'm saying, this is not 100% true, but I don't want to get too complicated right away. So, so please note that this is not 100%, but I'm going to go over why it wouldn't be 100%. Okay. Because it could have a cation that's acidic. Okay. So there's different things that can happen, but if it has an anion, that's the conjugate base of a weak acid, then generally the salt will be basic. If it has a cation, right, that is the conjugate acid of a weak base, then it'll be acidic. So we talked about this already. So let me just give you an example. If it has an anion that's the conjugate base of a weak acid, for example, fluoride, that's the conjugate base of a weak acid, or acetate, okay, then the salt will be basic. If it has a cation, that's the conjugate acid of a weak base. So for example, NH4 plus, like NH4Cl, okay? Or it could be CH3, NH3 plus. If it has a cation like that, then the salt will be acidic. Okay, so I'm going to, so that's acidic and basic. Okay, now here's another thing, is that many cations and anions are neutral. Okay. And let's try to remember back. Remember, we talked about how if you have very strong, we'll just say strong acids. Strong acids. Remember that the strength of the conjugate base is less when the acid is strong. So the strong acids, and I'm talking about HCl, HBr, HI, HNO3, H2SO4, and HClO4. These are the 6 strong acids. These have conjugate bases that are neutral. Because these are very strong acids, they have very weak conjugate bases. So these have conjugate bases that are neutral. So what is the conjugate base of HCl? Cl minus, that's right. Conjugate base is Cl minus, is neutral. Okay, so all the conjugate bases for all of these things, all the conjugate bases are neutral as well. So bromide is neutral, etc. Okay, this one is a little hard. What would the conjugate base be here? If you take away an H plus, what do you end up with?
HSO4.
Yeah, but don't forget the charge, right? Because you're taking away a plus, so you're left with a negative, okay? But that's right, good. Okay, so all of these ions that pair with H in strong acids, they're all neutral. They're all neutral, okay? And now we also have another fact. Oh, so let me write that down. Let's see. The anions of strong acids. And remember, that's the same as saying the conjugate bases of strong acids or the deprotonated acids, or the anions of strong acids or conjugate bases of strong acids. Either way, this is like saying the same thing. Are neutral. Okay, so another thing, another category that's neutral is cations. Those are positively charged particles that pair with hydroxide in strong bases are neutral. So, for example, we have sodium hydroxide is a strong base. So the sodium ion is neutral. It's a little harder to show this, and this is Gen Chem, so I'm not going to bother. But you should know that cations that pair with hydroxide in strong bases are neutral. And remember, in the periodic table, the first 2 columns of metals all form strong bases. So these cations are neutral. They strong bases with hydroxide. The hydroxide is what makes it a base. So calcium hydroxide, okay, in the second column of the periodic table, that's a strong base. So calcium is neutral. Okay, so all those metals in groups 1 and 2. So that's the alkali metals in group 1, and then the alkaline earth in group 2. I don't want to talk about the other metals. It's not Gen Chem stuff. Okay. So I have an activity, activity 10, somewhere over here. Here it is. And what this activity is figuring out if certain salts are acidic, basic, or neutral. Okay. So let's think about this. NaClO. Okay. So what do you do? What is the first thing you have to do here? You're given a salt. This is a salt. It's got a positive charge ion and a negative charge ion. So what you need to do first of all is you need to identify the ions. So the cation is sodium ion. The anion, well, you know sodium is +1. You might not know what the ClO ion is, but it has to be -1 because they have to balance. So we have two ions here, the sodium ion and the hypochlorite ion. I think that's what it's called. Hypochlorite, yeah. All right, so sodium, is that acidic, basic, or neutral? Based on what I've just talked about. What do you think? Neutral, exactly. Neutral, because it pairs with hydroxide in a strong base. So that's neutral. Now, what about ClO minus? So you have to ask yourself the question, is this the conjugate base of a weak acid? How are you going to figure that out? What would that acid be? What is the conjugate acid to ClO minus? What do you have to do to ClO minus to make the conjugate acid?
Add a H+.
Right. So it would be HClO. So, okay, so then you have to look at the chart. So you go to your acid dissociation chart. Oh, I think I actually have it on that. I think I have it right here. Look at that. Okay, so here is the chart. And you're looking for HClO. And there it is. So that means HClO is a weak acid. All right. So that means ClO minus is a conjugate base of a weak acid. So it's basic. So ClO minus is basic. So the salt NaClO, this ion is neutral. And then you have basic ClO minus. So, well, it's going to be basic. It's basic. Okay, that's how you figure this out. So that means, get rid of this thing for a minute, that ClO minus hydrolyzes to produce hydroxide ions. ClO minus plus water, reaction with water, accepts a proton to give HClO and OH minus. There is your hydroxide ion. Okay. And sodium does not hydrolyze because it's not acidic or basic. It doesn't react with water. It just sits there. So in a solution, the sodium ion just sits there. Well, it doesn't just sit there. it forms those nice ion dipole forces with water, but it's not reacting. It's just being. Okay. Ah. Get some more room. I can see I'm taking tons of room here. All right. Let's try the next one. MgNO2 So I think I'm going to copy my base chart. I got to push that button. Oh, wrong one. Okay. Okay, so now we have magnesium nitrite. I can't get the color I want. Just want black. Oh well. Okay, what about this one? What ions do we have here? What's the Mg? What's the charge on that?
Positive.
So positive what?
Positive.
2.
Yeah. And then we have two NO2 minus ions. So we're considering the NO2 minus ion. All right, so what about the magnesium ion? Acidic or basic or neutral? Well, it's a metal. It's in the first two columns of the periodic table. Magnesium hydroxide is a strong base. So magnesium pairs with OH minus in a strong base. And so it is neutral. Neutral. What about nitrite? Is this acidic, basic, or neutral? So you have to ask yourself the question, is nitrite the conjugate base of a weak acid? You have to figure out the answer to this question. What does it look a lot like? NO2 minus. It looks a lot like NO3 minus, but it's not NO3 minus. NO3 minus, if you scroll back a little bit, NO3 minus is the conjugate base of a strong acid, so it's neutral. But NO2 minus is not NO3 minus. If we look at the chart here, here is HNO2. HNO2 is a weak acid. So that means that NO2 minus is the conjugate base of a weak acid. So it is what? Basic. Okay. So this salt here, NO2 minus, is basic. See below. Okay, so that means MgNO2 is basic. All right. Somebody must have a question. I would have a question if I was studying this in school at this level. Well, if you have a question, it'd be great if you could ask it. All right, let's see. Okay, let's go back to the notes. Okay, now what about this one? This has the calcium ion and the nitrate ion. I just got through talking about nitrate. Is this the conjugate base of a weak acid? What's the answer to that question? We just answered it.
No.
No. And that's because it's the conjugate base of a strong acid, HNO3. So it is neutral. Also, calcium. We just did calcium. It pairs with hydroxide in a strong base. So it is neutral. So this salt is neutral. It has two neutral ions. Okay, now this one's a little different. So I want you to look at this and think about what the ions are involved here. Okay. And one of them I think you could get right away is from this. What would the ion be? Cl minus. Yes, excellent. Somebody said that. So that should help you figure out the formula of what's left. So it would not be proper to write it like this. What is missing here?
A charge.
And that charge is
Positive.
exactly. If you have the negative on the chloride, you have to have a positive on the rest. And then, you have to think, okay, what is this thing? Oh, it's got an N in here. It's based on based on ammonium, right? It's not NH4 plus, but it's got that other group there. Okay, so CH3NH3 plus. Okay, let's take a look. If we look at our chart of bases, weak bases, here is CH3NH2. CH3NH2 is a weak base. The conjugate acid of CH3NH2 is, well, just add an H plus. It's CH3NH3 plus. And that's what this is. See? Okay. So this guy here, which we would call methyl ammonium, but don't worry about that. This is the conjugate acid of CH3NH2 in this chart. So, and that's a conjugate acid of the weak base. So it is acidic. Okay. Now, what about chloride? Is that acidic, basic, or neutral? Is this the conjugate base of a weak acid?
It's neutral.
It's neutral. And that's because it's the conjugate base of a strong acid. So that makes it neutral. So the salt, CH3NH3Cl, is acidic. Okay. By the way, this is not on the test that I'm sending out sometime tomorrow or the next day, due in a week. Okay. So here's another part of this activity. And this part is a little, it shows that there are complications that can arise. Remember I told you that if a salt has a cation, as an anion, negatively charged ion, that's the conjugate base of a weak acid, that it's basic. Well, that's not necessarily true, because we have some salts that are more complicated. This one, NH4NO2. We have two ions here. We have the ammonium ion and the nitrite ion. Okay, so now we have a situation where this ion here, this is the conjugate base of a weak acid. So it is basic. But this guy is the conjugate acid of a weak base. So it is acidic. Oh, what do we do there? That's tough, right? Well, there is a way to deal with this, because what we can do is we can calculate the Ka for NH4 plus and compare it to the Kb for NO2 minus, and the larger one wins. So that's a little complicated. And I don't think I'm going to say much about that this semester, but I just want you to know why these would be more complicated. And so that's one. And then there, look at the rest of 10b, and you will see that there are some complications there. All right. There's a little bit more that I want to tell you, but I want to also tell you that I have this reading. So what I want to talk about next is how to find the pH of some salts. Okay. And I have another page in that activity handout for you to look at with this, and it goes through a whole set of steps that you use to do this. And I'm going to do an example now. So let's see. So here, what is the pH of calcium? What's a 0.1 molar solution of CaNO2 2. This has calcium ions, which are neutral because it pairs with hydroxide, and NO2 minus ions, which are basic because it's the conjugate base of the weak acid, HNO2. So we know it's basic, but now we're asking for some quantitative information. So how would you go about figuring out the pH of this solution? So the first thing you would have to do is say, okay, 0.1 molar of calcium nitrite is, you have to multiply that by 2 because you have 2 nitrites for every formula unit of this. That's 0.2 molar of the nitrite ion. And we know because nitrite is the conjugate base of a weak acid that it hydrolyzes. It reacts with water in that sort of base dissociation type reaction. NO2 minus plus water. What does it go to? It's the type of reaction we've sort of been writing all the time here. Anybody? If it's a base, it's accepting a proton. So what does it lead to? By the way, this isn't on the test. What I'm doing today is not on the test. Okay, the cutoff is kind of from yesterday.
Is it going to be on the next one, the last one?
Yeah, it'll be on the last one with thermo. It'll be a little bit at the end of acids and then thermo. Thermo will be the last 3 classes. I don't think I'm planning not to teach new material on May 3rd. I hope I don't need to use it at all for that because, yeah, I just think it's too much, but anyway. So this reaction, so this is a base, it's acting basic, right? It's a conjugate base to a weak acid. So you end up with HNO2 and hydroxide. So this is how you start the problem of how to find the pH of certain salts. So this is, what is the pH of this salt? And it's going to be an ice problem. Okay. Oh boy, I'm way off scale here. Oh well, what are you going to do? All right, so for the ice problem, all right, so we'll start with 0.2. This is liquid. You don't worry about water ever here. 0. Minus X. All right. I think I'm going to stop here. I think that's enough. I'm tired, so you must be tired. I think it's overload for now. So next class is important. Next class is very important because we finish this topic of salts, and then we do buffer solutions. And buffer solutions are really important. And actually, the lab we do next week is on buffer solutions. And you won't know what is going on unless you come to class on Monday. So I'm going to be mailing a test out, and I'll make an index for it. I'll be available for questions. I know it's the end of the semester. Just try to keep going and chip away at it, And if you have any questions, you could stay behind, or if you want to talk to me privately too, I can do a Zoom session anytime. So let me know. Hang in there, okay, people? Yeah. All right.